We know that a temperature difference causes heat transfer to occur. While this seems like a simple idea, there are lots of ways that heat transfer can be affected. There are, however, only 3 ways that the transfer itself can occur. Conduction occurs when a hot object is in contact with a cooler object. When a fluid warms, the particles expand and the density decreases. This causes the fluid to rise, and as it moves away from the heat source, it cools, becomes more dense, and sinks. This is the idea behind convection. Waves, such as microwaves and infrared waves, can also transfer energy in the form of heat, and this is known as radiation. When a material comes in contact with something warmer than itself, the particles from the warmer object are able to transfer more energy to the particles of the object. This is accomplished because the particles are moving fast and are colliding with each other. If someone is running along and collides with someone else, then the someone else gains some of that energy and moves faster as a result. Say that someone else is at the edge of a group of people. He may bump into another someone else next to him and transfer some energy to that person. This is what is happening during conduction. As the particles collide with one another, their kinetic energy, and therefore their temperature, increases. This continues on until the system has reached thermal equilibrium. The rate of thermal conduction depends on 3 things. First, it depends on what substance you have. Metals in general conduct heat much more efficiently than nonmetals. We represent this as K. An object with a high surface area is going to conduct heat at a faster rate, while the thicker objects will conduct it more slowly. So the rate of conduction also depends on the area and the diameter of the object. Finally, the temperature difference across the system will affect the rate of conductivity. If you have a lower temperature difference, you're going to have a lower rate of conductivity. If you have a higher temperature difference, the heat will move much more quickly. Some materials do not conduct heat well at all. These are called insulators, and we use them just as much as we use conductors. In the wintertime, you turn on your furnace, and you do not want that heat escaping to the cold outside. One way to help keep the heat in is by using insulation within the walls. Not only does insulation have a low thermal conductivity, but it is also fairly thick. This ratio of thickness to thermal conductivity constant is known as the R factor of a specific insulation. Suppose a styrofoam box has a total area of 0.950 meters squared and walls with an average thickness of 2.5 centimeters. The box contains drinks at 0 degrees Celsius. Inside of the box is kept cold by melting ice. How much ice melts in one day if the outside temperature is 35 degrees Celsius? Wow, what do we know here? Our area is 0.950 square centimeters, and the walls are 2.5 centimeters thick. The ice starts at 0 degrees Celsius and ends at 35 degrees in one day. We can look up the thermal conductivity constant for styrofoam, and that turns out to be 0.010 joules per second times meters times degrees Celsius. Pay careful attention to the units used, as we need to be sure that those are the same units in our calculation. So really what we need to know is what is the actual amount of energy that is being absorbed by the ice. So all we have to do is multiply by T on both sides, and we can rearrange for that. There are 86,400 seconds in one day, and we can convert centimeters into meters. We find that the rate of heat transfer is 1.15 times 10 to the 6th joules per second. Now we are looking for the mass of ice that melts over the course of a day. So we can rearrange our formula for the latent heat of fusion, and we find that we have 3.44 kilograms of our ice melting. Convection transfers heat energy through the movement of fluids. The buoyant forces associated with heated fluids cause an overall circulation through a system. When air is heated, for example, the particles expand, and we see a decrease in the density. This causes hot air to rise. Convection is responsible for circulation in the atmosphere as well as the ocean. This is also the mechanism that your body uses to cool itself. Describing convection mathematically is a bit more complicated than describing conduction, but we can look at some overall heat transfer problems to get an idea of what is actually going on. Suppose a house has dimensions of 12 meters by 18 meters by 3 meters, and all the air is replaced in 30 minutes. Calculate the heat transfer per unit time in watts needed to warm the air 10 degrees Celsius. So the idea here is the air inside the house is being replaced by convection alone. Ultimately, we are looking for an amount of heat transferred over a certain amount of time. To find heat, we can use our heat capacity equation, but we would need to know the mass of the air, the specific heat of the air, and the change in the temperature. Well, the temperature we were given. Mass we can probably find in a roundabout way since we were given the dimensions of the building and can determine its volume. And air-specific heat is a value we can look up. So mass we can find since we know the volume and look up the density of the air. So we find 836 kilograms of air in our building. Using our specific heat equation, we determine that 8.36 times 10 to the 6th joules of energy are transferred out of the house. Now we're looking for the rate that it's moving, so we just need to divide that energy by time. Since it is specifically asking for watts, we do need to convert that 30 minutes into 1800 seconds before dividing. This gives us 4,644 watts of energy. This is actually a pretty high turnover, and newer construction shoots for a minimum of 2 hours to replace air in an entire building. So a person produces heat at the rate of 120 watts when at rest. At what rate must water evaporate to get rid of all this energy? Well, we know the rate of energy transfer is 120 watts. We also know that the energy involved in a phase change, specifically changing from liquid to a gas. This means that we would want to use the equation for latent heat of vaporization to figure out the amount of energy that is lost. Now we are actually looking for the rate of evaporation. Since it is not specific as to what that rate should be recorded in, we can use what we have in our equation and solve for mass per unit time. The latent heat of vaporization of water is constant that we look up, and from here we find that we have 0.0494 grams per second. Okay, so grams per second doesn't really give us a good idea of how much that is. If we convert it to grams per minute, we find that we lose about 3 grams per minute. This seems like it would be reasonable. 3 grams isn't probably something you would notice on a normal day if you were at rest. If you ever just sat in the sun or in front of a fire, you've felt the heat. These are examples of heat transfer by radiation. In this situation, the sun and the fire are both emitting energy in the form of electromagnetic waves. The big difference between radiation and conduction, or convection, is that radiation energy can be transferred even when there is no medium for it to move through. All objects emit and absorb electromagnetic radiation. The color of the object has a lot to do with the rate of heat transfer. If you have ever stood on a black asphalt road in the summertime, you have experienced this firsthand. Simply stepping onto the gray sidewalk next to the road has an enormous effect on how much energy you feel. This is because black objects absorb radiation more than light-colored objects. White tends to reflect the energy and so does not absorb much in the way of heat energy. Interestingly, when the sun goes down, the black asphalt will be the first to cool as well. Not only does the black absorb more efficiently, but it also radiates more efficiently. If you were to wear a black t-shirt on a hot summer day, while out in the sun you would probably feel a lot warmer than someone wearing a white shirt. But if you were to stand in the shade, your shirt would cool you more quickly because black is also a good radiator. The power radiated by an object is determined by its temperature. In this equation, A represents the surface area of the object. This makes sense that larger objects will be able to radiate more energy or cool faster. T represents the temperature of the object. Take a good look at that exponent. We are looking at temperature to the 4th power. You just don't see that anywhere else. The radiative power of an object is dependent on the temperature to the 4th power. The E in the equation refers to what is known as the emissivity of the object. This is just a measure of how well it radiates. The lower the number, the less the object is able to radiate. For example, a shiny object such as a mirror or snow cover would have an emissivity closer to 0. An object more on the black end of the spectrum will have an emissivity closer to 1. Sigma is just the constant that holds it all together. And now this law can also describe the net rate of heat transfer by radiation simply by looking at the change in temperature.